In this video, we're going to explore the reduction of alkynes towards synthetically viable alkenes that are cis and trans. If you recall, Chapter 6, we saw the hydrogenation of alkenes using hydrogen and platinum. That gave us alkanes. And here, you would think maybe, just maybe, we could make a cis alkene and have the reaction stop there, because cis alkenes are viable synthetic targets that are very valuable. Sadly, this reaction will not stop here, no matter what you try to do. The alkene will react just as it did in Chapter 6, and it will give us an alkane and an element of sadness, because alkanes are dirt cheap and not very valuable, and this is the worst way to make them. So, even if you try to control the stoichiometry to stop at the alkene stage, say you tried saying, I'm only going to use 1 mole of this for 1 mole of this, you're probably just going to get about a ½ mole of this. So, not a useful way to make a cis alkene. Before we move forward, looking at reactions that can give us cis alkenes and the equally valuable trans alkenes, let's look at isotopes of hydrogen. These isotopes all react the same as hydrogen. They have been used successfully to determine the nature of reaction mechanisms. And I want you to note that whatever hydrogen can do, these isotopes do the same chemistry. And the only thing that is different is they have a different mass than normal hydrogen, and they react at slightly different rates. We will not focus on that last fact. The normal isotope of hydrogen, don't have to talk about that. That's the one you find on the periodic table. Deuterium does contribute to the mass of hydrogen. That's why it's a little higher than 1. There's the symbol for deuterium in terms of the isotope symbol, and its short form is D for deuterium. Tritium has 1 proton and 2 neutrons in its nucleus, giving a mass of 3, and its symbol is T. So these will come up. They will take the place of hydrogen, and you'll see why we need to have them very shortly. Let's look at a more useful catalytic hydrogenation reaction in 7.6b, one that gives us access with a syn addition of hydrogens to a valuable cis alkene. And we're going to start by learning the chemicals that have to go with hydrogen. Platinum didn't do the job clearly up here. There was a chemist named Lindlar who developed a series of catalysts, and one of them worked. He was much like the Edison of his time with hydrogenation, and his combination ended up being palladium metal, which in effect is actually more reactive than the platinum. It was embedded on calcium carbonate, which is like chalk particles, and he added this to tune down the catalyst, lead 2 sulfate, and that combination is now known as Lindlar's catalyst. And it gives us access to a cis alkene. Syn addition, you're not responsible for the mechanism. Let's look at some things. How can you tell there's a syn addition if you started with a terminal alkyne? If you have a terminal alkyne, you're going to have 2 H's on the end when you're done. No way to know if the new one is syn or anti to the carbon group. For example, if we used H2 in Lindlar's catalyst with this terminal alkyne, we get this, and there's no way to know that it's syn or anti. If we use deuterium instead of hydrogen, using the same Lindlar's catalyst, we can use spectroscopy to determine these deuteriums are indeed on the same side, and the old carbon and hydrogen groups are on the other side. Keeping in mind that Lindlar's catalyst here is quite expensive, and smaller facilities such as community colleges can't afford to use them, so we need an alternative to using Lindlar's catalyst. So this reaction technique was developed using hydroboration protonolysis, borane, as we've seen before, and acetic acid will give the same result. A little cheaper and more accessible to undergraduate schools. Covered up in this box here, what would happen if we used borane in the first step and the deuterium version of acetic acid. It's actually not two steps, it's all together. And the mechanism will show what's going on. The alkyne is attracted to the more positive boron in borane, and it's more positive because it has a lower electronegativity than hydrogen. Hydrogen, as before, comes back to the more substituted carbon, and we get this result here. This is in fact the Markovnikov regioselectivity, where the more electronegative H is on the more substituted carbon, less electronegative B on the less substituted carbon. It also happened to be that both of these arrows happened at the same time, which resulted in syn stereoselectivity, both new groups on the same side of the alkene. Protonolysis is, as we saw it earlier, this proton is going to lyse off the carbon-boron bond like this. Carbon uses these electrons to make a bond to deuterium. Acetate leaves, giving this result here. Most importantly, you get your syn addition alkene. I flipped it upside down. I hope that didn't disturb you too much. And acetate and borane cation, they combine. You're not responsible for showing me side product mechanisms, but if you're curious, this is what happens, giving this result right here. But this is the important thing right here, making our alkene. So now we have access to cis alkenes from alkynes, and we need to have access to trans alkenes because they are equally valuable. Here is another useful synthetic target, a trans alkene. How can we accomplish it from internal or terminal alkyne? We can use sodium metal. You do not see that every day. This is a very dangerous chemical. Warning. Good thing this is a lecture course. Nobody gets hurt. It also uses ammonia. The role of ammonia here is both reactant. It actually provides the hydrogens and the solvent. The mechanism will be explored in another video. And what would happen if we had a terminal alkyne? How could we test to see the anti-delivery of the new groups? Here's sodium metal, terminal alkyne, tritiated version of ammonia, and the new H. Oops, I think I see a mistake. My apologies, I had not finished editing this molecule. You see the two new tritiums end up on opposite sides, thus proving we have anti-stereoselectivity here and here. If we did not use tritium, we wouldn't know if the new H here was the same as or different than this H here. And let's finish by summarizing, and then you can go and watch the video on the radical reaction of sodium and ammonia with alkynes. Big finish. How can we go from a internal alkyne to a cis alkene depicted here? We had a couple ways. We use a combination of hydrogen, palladium on calcium carbonate, and lead 2 sulfate. Or we could have done hydroboration with acetic acid protonolysis to get the same result. The way to make a trans alkene is to react with a metal from the first column of the periodic table and ammonia, and you get a transalkene. We learned how to make internal alkynes in our study of synthesis, and they're valuable. But alkenes with geometry are even more valuable. Trans and cis, both very valuable. And I hope you found this video on the reduction of alkynes to be useful, and I look forward to our next video.